These lectures cover the final topics in the Quantum Physics 2 course, which focus on elementary particles and fundamental interactions. Um, the lectures will be broken up into probably four lectures, after which we'll probably have our examination. The first lecture, that is the one that I'm doing today, is approximately the first 20 to 24 slides of a 60 lecture slide set. And it will focus on how do we determine the properties of particles, in particular measuring particle properties using collisions or using scattering, and some of the language and characteristics of fundamental or elementary particles and forces. The second lecture in the set will focus on the properties of our fundamental particles, quarks and leptons. And the third lecture will focus on the interactions between quarks and quarks and leptons and leptons and quarks and leptons. The nature of the interactions, and in particular the force laws and conservation laws. Then we'll finish up with an overview of what is called the standard model. Now that we know all of the language, we'll focus on what is now called the standard model, and a little bit of culture. That is that in the future, you'll be seeing talks in which people will show what are called Feynman diagrams, and these take a little bit of knowledge in order to interpret, so we'll go through them. The material for these classes can be found in Chapter 14 of Crane and in Chapter 10 of Townsend. Both of these chapters actually contain a lot more material than we can possibly cover in the time that's allotted to this segment of the course. So focus, please, on the actual material that we cover in the lectures. Although these chapters themselves are quite interesting to read. Particle physics is sometimes called fundamental physics because it's aimed at determining the fundamental laws that control the properties of matter on the most fundamental scale. I will, comment here that the physics of complex structures is every bit as interesting and fundamental, but the terminology, usually fundamental and elementary, is limited to particle physics. From what you've been hearing, most likely you might think that particle physics is driven by theory, but it actually has turned out in the history of particle physics that the big ideas have actually been driven by experimental surprises, and then theory delivers some insight in order to try to understand what those surprises are about. The past 20 years have focused more on theory than the surprises, but there have been some interesting and useful experimental findings in the past 20 years. I want to highlight that what's called high energy particle physics and cosmology are not settled science. There are a lot of questions. Towards the end of this class, I'm going to raise some of the open questions with you so you understand what there is left for you to do. It in fact could be that we've got it all wrong, in the sense that Newton got relativity wrong, and that a whole lot of new and original thinking needs to go into fully understanding the behavior of the universe. What we do know is that the current set of models is not complete. Everything, or various aspects of theory, are not tied together. General relativity is not linked to quantum theory completely and thoroughly at this point. But what we're going to do is review our observations and the nature of the theoretical structure that we have. An overview to start out. What we call elementary particles are particles that, to the best of our experimental ability to measure, behave like point-like particles. We do know that, for example, the effective wavelength of a particle gets shorter and shorter as you raise the energy of the particle. And what we found with these particles, with actually all of these particles, is that as we raise the energy, sort of hoping to find the structure of the object that we're scattering, objects that we're scattering with one another, is that to the extent that we can possibly determine, these particles scatter off one another as though they have no spatial extent, as though they are point particles. Then there are what at one point were thought of as fundamental particles, but are now known to be made up of this set. This elementary particles consist of the quarks, the leptons, the force-carrying particles, which are called gauge bosons, photon, gluon, W, and Z, and the scalar boson, which moderates the Higgs force, is called the Higgs boson sometimes. Right. Then there are what we now know to be composite particles. We thought they were fundamental half a century ago. Those particles are the hadrons, which are made up of quarks, mesons, I'll be explaining what those are, and baryons. The best known baryons for us are the proton and the neutron. Bary refers to heavy, so these are heavy, nominally heavy particles composed of quarks. Then, of course, nuclei are composed of baryons, nucleons, and atoms are composed of electrons and nuclei. Molecules are composed of atoms, and solids are composed of molecules and atoms. Then in addition, in solid-state physics in particular, we have a whole host of interesting quasi-particles which behave like fundamental particles, but we know that they are not. They are particles or groups, congregations of particles that behave like fundamental particles. Those include, for example, an electron traveling through a solid. It does not have the effective mass of an electron, but it behaves like a particle that has a certain mass and a certain dispersion relationship. Solitons in optical fibers, excitons in semiconductors, the Hall we've talked about, magnons in ferroelectric materials, phonons are vibrational quasi-particles, plasmons and polaritons, which are things which are quasi-particles that Professor Wirtz actually puts a lot of effort into studying. Our tools to actually perform the experiments and attempt to understand what's going on started with actually photochemistry. Well, in some sense, that's what you see. Try to observe carefully, and then you can believe what you actually see. Particles, energetic particles, and X-rays and gamma rays are frequently detected in ionization chambers, where a particle of interest comes in high energy and scatters off of electrons, for example, in an ionization chamber, ionizing the atoms and freeing up electrons. And then we collect the current, or we collect a pulse of charge that results from an energetic particle coming in and ionizing atoms in the chamber. A cloud chamber, I'll show you some images for this in a couple of slides, is one in which you make a condensed, it's actually not condensed, a vapor which is has a very high density of material that could condense, but it needs something to nucleate on. And when a charged particle comes through and creates some scattered electrons, those can induce either liquid vapor in the chamber to condense, making a trail of little cloud particles, right? If it's water, it would just be clouds, water vapor, turning into droplets. Or in a bubble chamber, the charged particle comes through and induces bubbles to form in a liquid, which can be observed then. This was a very useful technique early on to understanding the behavior of radiation. Scintillation counters observe light that is emitted when ionizing particle comes in and excites an atom or a molecule in the material, and then when the de-excitation occurs, we could see light. Cherenkov radiation from particles traveling through a region of space, a material, such that the charged particle, it has to be a charged particle, is traveling at greater than the speed of light in the material. That leads to an electromagnetic shock wave, which can be observed. If you ask about these things, I'll talk about them. Bremsstrahlung, we talked about when we talked about X-rays. If a charged particle comes shooting into a material and rapidly decelerates, then X-rays can be emitted. Pair production, I'll talk about in a couple of minutes. Actual nuclear interactions, for example, a particle can, or rather a nucleus can absorb a neutron and then be in an excited state of the isotope, and then gamma rays come out as a result. Or finally, I've got here, and there are other techniques. One of the techniques that was used to studying the energy of particles is actually to allow the particles to bash into a material that then heats up, and you measure the change in the temperature. And from that, you can measure the energy of the particle that bashed in. So lots of techniques and lots of fun engineering and physics in making tools that work well. There's an entire industry of particle physics which is aimed at making better and better tools. And in fact, Professor Brown is a master at making xenon, extremely pure xenon, for observing particle interactions. Those were our tools for measurement. What are our typical sources? Well, there's natural radiation. So for example, if we have radioactive nuclei, radon, for example, then those nuclei are going to be emitting energetic particles. If you have a collection of nuclei, they will emit energetic particles, and then we can observe the particles. We can observe the interactions of those particles with materials. Typically, radioactive nuclei only can release energies of order 10 million electron volts in an interaction. We saw that in nucleosynthesis in the previous lecture, and if you look at the energy levels of nuclei, you find out that that the high end is around 10 million electron volts, or 0.01 GeV, giga electron volts. I scaled everything here to giga electron volts because that's an important scale for particle physics, and it also happens to be the mass energy of one proton or one neutron. So close enough, good enough for particle physics, let's call it. Right? Okay, I did want to come back here and talk about cosmic rays. Cosmic rays are particles that strike the Earth's atmosphere and have their sources in solar nuclear events, or in supernovae, or other large-scale events, and eventually find their way to the Earth's atmosphere. At the highest end, cosmic rays have huge energies of order 1,000,000 GeV. Typically, let's say the most frequent rays that we can observe are of order MeV type energy, so much lower energies. And not many, but some fundamental particles were discovered as cosmic rays, as particles that originated in a solar nuclear reaction and then found their way to the Earth. In terms of experiments that we can directly control, though, actually, let me say one more thing about cosmic rays. Cosmic rays right now are actually a big subfield of particle physics that involve the search for dark matter, the study of the properties of neutrinos, because the greatest sources of neutrinos are solar, and I think that's, and extremely high energy cosmic rays. So this sub-area of physics is a very active sub-area of particle physics. Accelerator sources include, historically, the first sources were Van de Graaff generators, which you've played with. You rub a rubber belt against an insulator, and you can exchange charge and then transfer the charge to one end, and you can, by stacking up Van de Graaffs, you can get energies of order 20 million electron volts in order to study nuclear interactions, for example. The cyclotron was an early accelerator and could achieve energies of up to 1 GeV, up to the proton energy. But if you want to study the structure of protons, for example, you have to have much more energetic particles to scatter off of the nuclei that you are interested in. And that's achieved with linear accelerators. The linear accelerator at Stanford, SLAC, has an energy of about 100 GeV right now. And then with synchrotrons, and in particular with hadron accelerators, we're able to achieve energies up to 5,000 GeV. Now, these are very frequently the energies of one of the particles in a scattering interaction. And therefore, from your studies already in special relativity that if one of the particles has 100 GeV, then the energy that's actually available for making new particles is much less than that, right? Because you have to change into a center of mass frame, and then the total energy is going to be quite a bit less. Here's just a visual reminder of what I said about the accelerators. So there are hadron colliders, all right? I'm going to go through some words later on. Hadrons are particles that are composed of quarks, and I will tell you about quarks in a little bit, so I'm sort of getting ahead of myself. And since the in-depth study of particles using accelerators, the typical hadron colliders, for example, have gone from far less than 10 GeV, so remember this is the proton mass here, up now to thousands of GeV, and most recently I looked and checked and found 5,000, almost 6,000 GeV. And then there are the electron colliders, and if you can collide a high energy electron with a positron, then you're in the center of mass, and so you're actually getting all of that energy into the reaction that you're looking for. Very energetic electron colliders are frequently used to study the substructure of nuclei, for example. So a little bit of theory to start off with, actually. Of course, you know already that when we teach you something in physics, there's actually something that's a little bit better that sits behind it, but is mathematically perhaps a little bit too difficult for you at this point, or that is perhaps a little bit more subtle to understand. So I want to tell you now that the Schrödinger equation is just a non-relativistic equation. And when we're studying particle physics and the structure of the universe, it turns out, we actually should use a relativistic equation. And one of the simplest relativistic equations to make a relativistic equation is based upon the relationship that you already know from special relativity, that the energy of a particle squared, the total energy, is equal to the momentum squared plus the mass energy. So we can do what Schrödinger did at this point, but now we're using a different energy momentum relationship. So what we can do here now is look at each of these things here and substitute the appropriate operator. So for energy, we have this operator, h squared, second derivative of the wave function with respect to time, all right? Because I've got e squared here, that's what it's going to be. Not e, but e squared, all right? If it were e, then I'd have minus ih bar, ih d psi dt, all right? I may have lost a 2 pi in here. We're not going to do very much with this equation, so I'm going to leave it as it is for now and maybe check it later on. On the other side, I've got my momentum, and this is the operator that we had for momentum, taking space derivatives. And then there's the mass energy, which doesn't have, it's its own operator, let's say. This equation is called the Klein-Gordon equation. And I should mention that this can be taken and was taken very shortly after the Klein-Gordon equation was established, was taken to the next step, including spin in the relativistic equation. All right. The only thing that I want to say about this now is that this is a linear second order equation that can be solved. Right now, we haven't added any potential in here. So this is just for a free particle, right, in a zero potential. And we can look for solutions to this wave equation, right? This wave equation actually looks a lot like the string wave equation, by the way, where psi would be a displacement. But let's just look at this equation as it is. We can apply separation of variables and obtain the separated equations for space and time, assuming a product solution. And now we take a quick look at that product solution, the form of product solution. And because the energy appears as a squared quantity, it means that we can find solutions that are both positive energy and negative energy. And one question we should ask ourselves is, okay, you have a free particle in empty space. How can that particle have negative energy? What does it mean? Well, let's just take a quick look at the wave equation itself. And we see that for a particle with positive energy, moving in the positive x direction, the wave that results from solving that equation is the familiar traveling wave that we know, and I'll write it out in terms of the energy here, right? So that's a positive energy, and this object is traveling in the plus x direction. If now I take the same solution and look for the solution for the negative energy, all I'm doing in here is substituting minus e, right? There are two ways to look at this. One is that these two negatives cancel one another out, and that's a positive energy particle traveling in the opposite direction, right? So same equation, all right, different solutions where same form of solution where the negative energy particle behaves like a particle that's traveling in the opposite direction from the solution. The statement here is moving in the plus x direction, right? So a negative energy electron is equivalent to a positive energy electron moving in the opposite direction. Or another way that people talk about it is a positive energy electron moving backwards in time. We're going to come back to this when we talk about Feynman diagrams later on. Does it really move backwards in time? Well, let's just say that the mathematical solutions look the same. That previous slide where we have solutions, the same solutions to a given equation, to the Klein-Gordon equation, with positive and negative energies that imply particles that have different properties. I'll just call them different properties, led to the proposal of what is called the antiparticle. A particle that, if you solve more carefully through, you find has an opposite charge to the particle if it has charge, and has these different behaviors. And here's a nuclear reaction experiment that was performed in 1932. I mentioned, by the way, that the Klein-Gordon equation was actually proposed in 1926, which was actually prior to the acceptance of the Schrödinger equation. But the Schrödinger equation worked so well to predict properties of systems that the Schrödinger equation became the one that everybody used for solving atoms, for example. But the more careful solution to Klein-Gordon and then the Dirac equation with spin leads to better and deeper fundamental understanding of the behavior of space and time. What Carl Anderson did was to actually just put radioactive material over here, and that was incident, and then the radiation that came out of it, the gamma rays that came out. So he put in some shielding, gamma rays that went through the shielding, then hit a thin lead sheet here, and this lead sheet was in a bubble chamber where when a reaction occurs, when a charged particle moves through the bubble chamber, it ionizes atoms in the chamber and leads to the formation of bubbles because it's a critical liquid. And so here, it looks as though we have our gamma ray coming in. You can't see the gamma ray because it's not ionizing that much. And then it interacts with the lead, and then something comes out. And there's a magnetic field here, and we end up getting two equivalent particles. And we can determine that one of these particles is an electron, and then the other one seems to have the same charge to mass ratio, but it has the opposite charge because it curves the opposite way in the magnetic field. That thing is called a positron. And when a positron meets an electron, the two annihilate and gamma rays come out. This is a case where gamma ray comes in and creates matter-antimatter pair. There's a cartoon of this on the next slide that I. So here's the idea. I think I probably got this out of, actually, I don't know where I stole this from. Gamma ray comes in, hits the lead sheet, forms a particle-antiparticle pair, electron-positron pair, and because of the magnetic field, the two particles curve in opposite directions in the field. So that's just stated here. Gamma ray comes in, it actually interacts with the nucleus, and what comes out is electron-positron pair. They have equivalent energies, and they obviously have opposite charge because of curvature in the magnetic field. And we can also then measure after that, when they annihilate with one another, gamma ray comes out, we can measure the energy of the gamma ray, and it comes out to be 1.022 million electron volts, which is twice the mass energy of the electron. So there's an example, just to start out, with some relatively simple theory that made a weird prediction, but then that prediction was confirmed through experimental measurement. That's the way, largely over the history of modern physics, theory and experiment have worked together. I'm going to take a little bit of a detour now and talk about some of the interpretation and experiments that one does in order to study the properties of fundamental particles. And one of the most frequently used tools is what is called scattering or attenuation experiments, where we shoot one particle into a target, and then either we look at what comes out, or well, basically that's it. We look at what comes out. So the analogy has been drawn in by solid-state physicists that what particle physicists do is that they want to understand, for example, how a well-crafted microelectronic system works. And so what they do is smash two microelectronic systems together and then look at what comes out and try to figure out what the structure was. The actual things that they're smashing together are less complex, so a lot more can be inferred from the experiments. So I want to talk about the experiments, the way that experiments are interpreted first. So what are some of the things that can happen when two things are smashed into one another, when things collide? Some of the possibilities that the incident particle just scatters from the target particle, we're talking about particles here, transferring momentum, but doesn't cause any excitation. And examples of that kind of effect would be Compton scattering or Rutherford scattering. Compton scattering is gamma rays scattering off of electrons, and Rutherford scattering is alpha particles scattering off of nuclei predominantly. Other thing that can happen is that it's still just scattering, but the effective wave of the incident particle scatters off of or interacts with the target particle, and we end up with a diffraction pattern. Another set of possibilities occur if the incident particle actually causes some excitation of the target. So an example of that would be an incoming photon actually exciting a transition, an optical transition in an atom, for example. We would call that photoelectric excitation, or excitation of a transition. And perhaps the, well, I'm going to leave that one. Perhaps a new particle could be produced by the excess energy. So for example, we shoot a gamma ray and it scatters off of a nucleus, but in the process an excitation occurs and an electron and positron come shooting out. And then we look at all the products that come out and we go, oh, we got something new here. The gamma ray has changed its energy, the nucleus has changed its energy, and these new particles have been formed. The common idea here in studying what's going on here is the idea of the cross-section. And I'm going to describe what I mean by cross-section in a little bit more depth on the next slide. It pretty much tells us what the probability of an outcome is. When I shoot an electron at a nucleus, does it just scatter by electromagnetic scattering without any loss of energy? Or does it excite electrons in the atom? Or does it actually scatter other electrons out? Or does it create new particles? There's some chance that each of these things can happen, but at certain energies, the chance of something happening can be much greater than another energy. So we have the concept of the cross-section for an event, the probability that something happens, which could depend upon the incident energy, for example, of the particles. So we've talked about cross-section before, but I'm going to go back through it now to remind you. Think about a bunch of tiny particles incident on a large hard sphere. We actually did something like this with light from the sun striking the surface of the Earth, right? The effect of cross-section for the collision between these particles and that physical particle there, if we just think of these as tiny balls, BBs incident upon a basketball, right? Then we ignore the size of the BBs typically, and we just worry about how big the basketball is. And then we ask what fraction of the BBs get scattered off in some new direction. Some of them hit here and go backwards, some of them scatter out like so, but only those that actually hit the surface do anything at all. So the effective overall cross-section for scattering in that classical case is going to be equal to the cross-sectional area of the basketball, right? Now, if in some large area A, there are n targets, so now I take this basketball and I put other basketballs around, then I can ask for many incident particles here, what fraction of them scatter, BBs, what fraction of them scatter off of a basketball? So that's the sort of thing that we're looking for at this point, and that gives us the total target area. I'll clarify a little bit more on the next slide. So the cross-section for a given process, so what we were talking about was physical scattering, but maybe we ask in the same vein, if I start shooting particles, photons, into a bunch of atoms, what's the probability that an absorption event is going to occur? So that we're going to relate to what we call a cross-section as well. The cross-section for any process is a unit of area, and it's proportional to that area, it's proportional to the probability of some occurrence for these particles being incident. So let's say I've got an incident flux of phi, all right? And I can think of that incident flux of phi as being a certain number of incident particles per unit time. And I'm going to divide all those particles into an area of A. So phi is particles per time per area, okay, which I'm going to write here as I over area. And so that I is the arrival rate of projectiles onto the area. The occurrence rate from a single target. So I've got a single target, and then we ask, what's the probability that all that flux of particles is going to result in something happening, let's say a scattering event. So I'll label that occurrence rate, how frequently does that occur, right, as the flux of particles per area times the cross-section. Or I've got the rate at which particles arrive into the area times the cross-section of a single target divided by the overall area of all the particles over which all the particles are coming in. And if the target has capital N non-overlapping target particles, then the occurrence rate is going to be equal to the rate of arrival of particles times the number of targets in the area times the cross-section, all right, per particle. And because we want the rate, it's the cross-sectional area of the targets divided by the overall area. Because remember, the flux is arriving over the entire area. So that's what the concept of a cross-section is. It's a question of, if I have n particles over some area, what's the probability, what's the rate at which an event is going to occur? So cross-section relates to probability that something's going to happen. But it actually is an area. So one experiment, one of the easiest experiments to do, no experiment is really easy, but is to shoot a beam of particles, maybe light, for example, at a sample, and then try to figure out what comes out. We can measure what comes out the other side, and then relate that to some physical properties of the sample. What we're going to do is conceptually make some slab of material. So I've got a thick slab of material, but I'm going to chop it up into extremely thin layers of thickness dx, right? And we're going to make dx small enough that the number of target particles in a thin slab dx is going to be relatively small, so that we don't have any particles stacked on top of one another. The targets are well separated. So we'd like the product of the number of particles per unit area times the cross-section to be much smaller than the actual target area. All right. So the number of particles is, that's actually number of particles, not per area, is equal to, it is per area, I take it back, is equal to the number of targets per unit volume, which we'll call rho, it's the density of targets, right, times the thickness of the slab, dx. And so if we think about particles incident upon a very thin slab here, then the change in the flux of particles passing through a very thin slab, dx, is going to be the flux that's incident on the surface of that slab, which we'll call phi at x, all right, times the number of particles per unit volume, times the cross-section per particle, times dx. So number of particles per unit volume times dx gives me number of targets per unit area, targets per area, times an area is dimensionless. Okay. The solution to this differential equation is that the flux as a function of distance through the material is the incident flux, e to the minus target particle density, cross-section per target particle, times the distance through the material. This, by the way, is frequently called Beer's law in chemistry. The product rho times sigma has dimensions of inverse length, and that product rho times sigma is called the attenuation constant for the material. So here's an example of the measurement of the cross-section for, I've got to think, scattering photoelectric pair production, total cross-sections for lead. It's gamma rays incident on lead, right? So we go from low energy photons to high energy photons. At low energy, we have photoelectric excitation of electrons in states in the lead, right? So my photons coming in can cause excitations from state to state. There is an overall electromagnetic Rayleigh scattering cross-section. So independent of the details of excitation in the material, just the fact that I've got electrons in on an atom, when a electromagnetic waves comes through, it's going to cause the electrons to polarize. So not an excitation, but they're just going to polarize. The state's going to change slightly, and that's going to cause scattering. So here's a scattering cross-section, right, as a function of photon energy. We can measure the cross-section for photoelectric excitation, right, which is this curve here. And then there's a cross-section for pair production. And let's say experimentally, all we know is that the cross-section looks like this as a function of energy. And then we look at this spectrum and attempt to interpret what's going on. So there's a lot of information in a curve like this, and that can be used to develop the models for what the interactions actually are. So that's the sort of experiment that we're talking about when we are talking about scattering experiments. In this particular case, we're measuring what is transmitted in a collimated beam through the material and inferring the properties of the material from that transmitted beam, right? We can do other types of scattering experiments, which I'll talk about shortly. But here's another cross-section measurement. This one, I actually don't remember what the interaction is. It looks like it's a gamma ray on protons. I chose this simply because it shows a variation in the cross-section by orders of magnitude as a function of the incident particle energy. And then up here are the mechanisms that give rise to the various terms in the cross-section, right? So interpretation of a curve like this, where we observe what are called resonances in the cross-section, tell us something about what excitations can occur. And the important note here is that this is a gamma ray on a proton, right? So if protons were structureless, then you wouldn't expect to see excitations within the spectrum of protons. Sometimes it will be the creation of new particles, but there's actually more structure here than we would expect in this spectrum than we would expect just from a perfect point proton. And here's the spectrum of absorption cross-section for gamma rays incident on neutrons, where we got the energy of the gamma ray here. So it is interpretation of curves like these that allows us to figure out what the structure and interactions of fundamental particles are. There's actually a lot more information than just measuring that spectrum as a function of energy. What we can do is I've got my target here. I've got an incident beam coming into a target, all right? And what we were measuring previously was how many particles come through. So we shoot them in, and then we put a detector over here, and we measure how many come through, all right? But what we could measure instead is at what rate are particles scattered out to a certain angle or into a certain direction. Usually the systems that we're looking at are spherically symmetric systems, and as a result, anything that gets scattered this way, we're going to end up with the same rate in that direction. So frequently, when we calculate what's the probability of something scattering into here, what we'll do is measure the probability of something scattering into an entire annular ring within a certain range of angles. What I am going to talk about on the next slide is the units that we use to describe this scattering event. The coordinates, if we use spherical coordinates, are the same that you're familiar with, but right now they're turned on their side. All right. So if we consider this to be the z-axis, then theta is the angle from the z-axis, and phi would be the angle as we go around the circle here. All right. So theta and phi. And typically we put a detector that just sort of sits out here, and we measure what is received into a particular detector. The fraction of incoming particles that get scattered out into a certain angular range here at, let's say, angle theta with a range of d theta is called the differential cross-section, and it's written as d sigma d omega, where omega is the symbol for what is called solid angle. I'm going to talk about solid angle on the next slide. There's a little bit of information here, but I'll talk a little bit more about it on the next slide. So what we're measuring now when we talk about differential cross-section is for an incident beam of particles, what's the probability that a particle gets scattered out into a certain angle theta with a range of d theta, okay, where that could go into any of the phi's, right? It can go anywhere around, but what's the probability that it gets scattered out into a certain direction, a certain angle from the incident beam? Students in a course at this level have seen in another course, usually a math course, ideas that are related to what is called solid angle, and they've been asked to do calculations, but my experience is that they don't really quite understand what it is that we're talking about. So I'm going to make an attempt here. All right. That I have found that introductory textbooks say, oh, this is hard, we're not going to discuss it, and upper level textbooks say, oh, you already understand all of this, so we're not going to explain it. So I'm going to insult you by explaining it. Here's an analogy. We define what we'll call the planar angle theta in radians as a ratio of the length of a circular arc, All right, I'm going to make a drawing now of a circular arc. So I've got a center of curvature here, and I'm going to make an arc out here at a distance r from the origin. Okay, we define the angle theta as the ratio of this distance here to the distance around the full circle that surrounds this. Okay, so this is our definition of theta now. The r shouldn't be here any longer. R just refers to the distance from the center here. And we're going to take a ratio of this distance to that distance. We need units, and so we actually measure this distance along the arc in units of the radius. You say, how many radii have we gone? And the distance around a circle is a total distance of 2 pi radians. So that's our measure for planar angle. I can't make a drawing for solid angle. I have a picture on the next slide that I will talk a little bit about. I can't actually make that particular drawing, but I hope you got the analogy there. We've defined that distance as 2 pi. Well, we measured the distance in terms of radians, and we found that that distance is 2 pi radii measured around the circumference. The solid angle is measured in units of what we call steradians. And it's defined, the solid angle, is the ratio of the area of a piece of a spherical surface divided by the square of the overall radius of the sphere. So we measure this area in terms of square radii, right? You already know that the surface area of a sphere is 4 pi r squared. So a sphere subtends a solid angle of 4 pi steradians around a point. I have a picture on the next slide, I hope. Yeah, here is an attempt to draw a spherical surface. I am searching, there we are, for my laser pointer again. Here we are. A spherical surface, so unfortunately it's a two-dimensional plot of drawing of a three-dimensional surface, but I hope you get the idea of what it is here. And a little element of area on that surface that I'm going to call dA. The area of a little element on that surface is going to be r d theta. All right, r d theta would be the distance along that path there, and then the distance in this direction here around like so is r sine theta d theta, sine theta d phi, where that angle is phi and this angle is theta. And so the area of that little area element dA is r squared sine theta d theta d phi. That would be the overall area. We're going to take the radius out of that calculation so that the total the total angle that is subtended in all directions is 4 pi steradians. So the solid angle subtended by that little bit of surface there is the area of that surface. I've written it where I've taken r to be the normal to the surface, so I'm taking the component of the area which is on the surface, right? But the way that we've drawn it, the area is a parallel. The area normal is perpendicular to the spherical surface. So this thing here would just be dA for an element on the surface over r squared, all right? So it's the component of that area, the fraction of the area that is perpendicular to the normal, all right, divided by r squared. And as I mentioned before, in spherical coordinates, that differential area is r squared sine theta d theta d phi. So the solid angle d omega, which takes the r squared out, is sine theta d theta d phi. And the total solid angle over the whole surface is 4 pi. And the unit is called the steradian. The probability that something scatters into some angle, right, would be related to how large the range of angle is, and we would measure that range of angle using steradians. Right? The scattering probability out into some particular angle, as I implied earlier on, is usually symmetric about the z-axis if our particles are incident along z. And so if my scatterer is here and my particles are incident on that like so, and I am interested in the probability that something gets scattered out into some angle theta, all right, like so, then I should actually be interested in the probability it's scattered into any of the phi's that correspond to that theta. So over here, I've got theta as well. All right. So very frequently we'll integrate around phi. And when we do that integral, then the solid angle, searching for my laser pointer again, there we are. Then the solid angle, subtended like so, all right, is 2 pi, the distance around that circle there, sine theta d theta, which you'll find in textbook is frequently written as 2 pi d cos theta, because sine theta d theta is d cos theta, or rather sine theta is d cos theta d theta. There's a minus sign in there, but we don't worry about that. I have some additional calculations here. If I've got a flat detector face, so I've got a spherical surface like this, spherical surface, but my detector face is flat, there are corrections that we would make for the perpendicular area, and I made that for you here in case you need it at a later point. Very frequently, our detector is pretty small compared to the overall solid angle. So frequently we have a situation like this where I've got my target and things are scattering out, and then I can only afford a detector that's that big, you know, a photo detector. Maybe it's a 2-inch diameter and it costs $3,000, right? And the closest I can get is a meter. And so this area here is really quite small as it subtends like so. In that limit then, the solid angle subtended by the detector is just the front area of the detector divided by r squared. So that's a nice simplification. I'm going to skip this slide, except to tell you that if I have particles incident upon a target and the primary scattering cause is diffraction, then it turns out that the probability of finding a particle as a function of angle is the Fourier transform of the transmission probability through the target as a function of position. But we're not going to do anything with that in this course. I'm just pointing out that it relates to stuff that you have learned elsewhere. Um, I put one fundamental result here, which was something of a surprise when the experiment was done. There were theoretical hints that perhaps this may be the case, but the actual observation had not been made, and that in this case here is this is a reference to an experimental paper that that came out in the late 1960s, 1969, where what these people did was to shoot high energy electrons at hydrogen, right? So the primary scattering that was occurring there was actually between electrons and protons. And at that point, some people would argue that protons were point particles, and if they were, then the only interaction would be electromagnetic, a Coulomb force, and you could easily predict what the intensity, what the scattering cross-section should look like as a function of angle and as a function of energy. And that is not what was observed. They had some hint, otherwise they wouldn't have done the experiment. There was theory that pointed in this direction, but they did the experiment to test. And I took a quote out of the middle of the paper. We observed the excitation of several nucleon resonances, whose cross-sections fall rapidly with increasing q squared. That's the exchange of momentum. So rather than angle, they measure the cross-section as a function of exchanged momentum. In the region beyond an energy of 2 GeV, there are surprisingly weak q squared dependence. That is, that you would expect the intensity to be falling off strongly as a function of transferred momentum, angle, but it doesn't. And that implies that there were point particles inside of this proton. The proton wasn't a single point particle, but there were multiple point particles. So these experiments and related experiments led to the following conclusions: that protons and neutrons have internal structure. And furthermore, they could determine that protons and neutrons, remember they just scattered off hydrogen, so there's just protons in there, for example. Protons and neutrons seem to have three scattering elements, three scattering centers within their structure. This then confirmed the theoretical and mathematical model that said that the existing particles pointed toward there being substructure, and those things that were scattering, the three, fit into Gell-Mann's model, where he had called those components that made up protons and neutrons, he had called them quarks. So this was the experiment that led to the confirmation that protons had substructure, and that substructure was a threefold substructure. So all of these experiments finally lead to a picture like this, where we have 6 fundamental particles that have properties associated with quarks. And in the next lecture, we're going to talk about the actual properties. So right now, I'm just going to tell you that there are 6 fundamental particles that we call quarks. And there are 6 fundamental particles that we call leptons. And for each of these fundamental particles, there's an antiparticle. So some people will say there's 12 quarks and 12 leptons. I would say there's 6 of each, and they're antiparticles. And as far as we can tell at this point, there are 4 force-carrying particles called the gauge bosons. There's the gluon, which we can't observe directly. Photons, which we can see, all right? So we can observe photons. Z bosons and W bosons. Gluons carry the strong force. Photons carry electromagnetic force. The Z and W bosons carry weak interaction force. And then the Higgs boson is a symmetry breaking particle that leads to the observation of mass. We're going to talk in more depth about these particles in the next lecture. But for today, that is it.